Hey there, welcome back. So hopefully you're still not dying from all the math. It'll be helpful if you have a calculator for this one, this particular problem. We're going to take a look at solving some problems and doing a couple of examples and kind of learning how to sort of identify variables, plug them in, use our equations and all that sort of stuff. The slide that I have up here is the same slide that I kind of ended the last one with, which is fine because it's got our equations all in one spot. I really strongly recommend that when you are doing your physics homework, take these equations and put them in like a little sticky note and just put them right there in your notebook as you're doing your work. So you've got them there to use. A couple of things to kind of remember about these equations or to kind of review about these before we start actually using them all. A couple of things to know about these equations. This top one that's up here, this one is really important that you can only use in very limited circumstances. We rarely use this one, but it does get used, but it only gets used during cases where there's no acceleration. As soon as there's acceleration, we cannot use this top graph because the graph's a slope. It's a little bit of a different kind of a different arrangement to it. So we can't use this one. This is one of our basic equations. This acceleration is velocity divided by time. And this equation and this equation are the same thing. They are the same equation. The only thing that they've done is taken delta V and turned it into VF minus VI. And then kind of done a little bit of algebra with it. But these two are the same equation. So again, if you want to remember one or the other, it's fine. This one's a little bit easier because it's in that final velocity format, which oftentimes is being asked for. This one, it's not as obvious that initial and final velocities are in there. So again, sometimes people like to use this secondary version of it rather than the top one. Your choice, the same equation. This third equation down here, again, to remind you, is that our area equation. It's our integral. It's the area under a velocity time graph, especially if it's got initial velocity and we know its acceleration to it. And then this last one up here is specialized because there ain't no time for that. If I could write, hold on. Ain't got no time for that. So this last one is specialized for those cases where you don't have time missing, right? This is the only of our equations that doesn't have time in of all of them. So it's got its own kind of set of uses to it. And this one is just an algebraic derivation of the previous equation. Believe it or not, they're all algebra, but they're all related to each other. So there's your kind of 4 to 5, how to 3, however you want to count it, kinematics equations. There are others as well, but these are the ones that we tend to use quite a lot. Okay, so in this particular equation, the most of the rest of this is actually about doing some practice problems. And I think I've got 4 or 5 different example problems to work through. So again, if you've got your calculator, that's helpful. And as we get going on these, you can kind of hit pause, kind of play along if you want to, because listening to this certainly is not the most exciting thing that's ever happened. But I do walk you through the problem so you have some idea how to use it. I'm going to recommend kind of a consistent story problem approach to all of these problems. We will continue to use this approach, especially as we get into more challenging situations like free fall acceleration, last of this part of this chapter, and as we get into force acceleration, collisions, and things like that come up in future chapters. So kind of practicing this set of steps is a useful step. So first of all, make sure that you always read the problem. Picture it in your head. That's what I mean by imagine, right? You should be able to know in your head kind of what's moving and how. Don't just look for the numbers and try to plug them in someplace. A lot of problems get made that way. So read the problem, kind of try to picture it in your head, then sketch the problem. And again, super simple, stick figures. You know, you've seen my pictures of my cars before, you know, something along those lines. There's my car moving to the right. Doesn't have to be fancy, but sketch the problem so you can go, it's moving this way or it's moving that direction. This will catch a lot of issues with negative signs that students have that when they forget to kind of include things like that. Identify your variables. Do you know what VF is? Do you know what VI is? Do you know what A is? That's what I'm talking about by identify your variables. Start to figure out what the pieces are and what they're called. Using the units can be very useful in this particular case. Remember that displacements have units in meters or some sort of version of meters. Velocities have units in meters per second. Times have units in just seconds. And then accelerations would have units in meters per second squared, something like that. Again, also looking for things where there might be inconsistent units, like you maybe have centimeters and meters, or where you have seconds and minutes. Really important to make sure that all of your units are consistent within a problem. You'll always have distances and times, but they should be the same unit of distance and the same unit of time. And then using your variables, once you have your variable list, is the great way to actually identify which equation do I use. A lot of students that struggle with this algebraically have a hard time, like all the letters and numbers start jumbling together. Oh my God, which one do I pick and how do I know? Right? Alphabet, number soup, no. Having your list of variables helps you identify which equations you could even possibly start to use, as opposed to which equations you can't use yet because you don't have enough information. So again, this is part of our problem-solving approach that we will use. Okay, example number 1. We've got a jogger here. Joni's jogging. She's starting at jogging at a velocity of 2.50 meters per second. If she then accelerates at a constant negative 0.10 meters per second squared, how fast will she be jogging when she's moved 10 meters? So we've got Joni, here she is jogging, whatever, it doesn't really matter. She's moving that particular direction. Her VI, right, her initial velocity is 2.50 meters per second. So that's her VI, is going that way, right? That direction. She then accelerates at a constant negative 0.10. So A is this way, acceleration negative 0.10 meters per second squared. So even though she's moving forward, her acceleration is somehow pulling her backwards. In other words, she's slowing down, right? And then how fast will she be jogging when she's moved 10 meters? So her displacement is that direction, D equals 10 meters, and it's positive, right? There's no positive or negative sign. You got to look carefully. So that's why I'm saying those are going to be positive. So my positive direction's to the right, my negative direction's to the left. What do we have in here? So list your variables out. I've got VI equals 2.50 meters per second. I have an acceleration of equal to negative 0.10 meters per second squared. I have a displacement of equal to 10 meters, 10.0 meters. What else do I have? I'm trying to find how fast will she be jogging when she's moved 10 meters. So when I'm looking for this part, my question now is I'm trying to find how fast she'll be at the end of the story. So that's got to be a VF that I'm trying to find. So VF equals question mark. So again, going through these few steps of identifying what you know and what you don't know can give you a hint to try to figure out what this is. Now, what I'm noticing, what I'm missing, is I don't have time. It's always the thing to look for. Because if I don't have time, there's one and only one equation that I can use. So you can go back to your list. I'll go back and do a real quick right here. There's only one equation that doesn't have time in it, and it's this bottom one. Do I have VI? Yep, it's given in the problem. Acceleration is given in my problem. Displacement, how far she's going, is given in the problem, and I don't have time. I'm trying to find VF for it. So that's the equation that I want to use. So I'll go back to my problem here. This is my equation. VF squared equals VI squared plus 2A delta D. It's important to make sure that you always write your kind of naked equation and then you start to plug the numbers in. In your homework, I'm going to ask you to do this. So make sure you write your variable level equation and then plug in your numbers. What do you have? What do you not have? Well, I don't have VF, so make sure to do that. Don't drop that squared sign, man. This is the one thing that students do all the time is they drop the squared. VI squared is 2.50 squared. Don't forget that. You need to have that on there. Plus 2 times A. Acceleration is negative 0.1 times D, which is 10. I'll come back and do Sig Figs at the end, right? So now it's just a matter of plug and chug. 2.5 squared is a number, 6.25. Where is it? Equals 6.25 plus 2 times negative 0.1 times 10 is plus negative 2. Don't forget your negative signs. Negative signs is the other big thing that students do wrong all the time in here, that they forget to square things, they drop those, and then they drop the negative signs. It's important. Remember, they're going opposite directions. That's critical for us. So 6.25 plus negative 2 is 4.25 is going to be VF squared. That means that you have to do a square root. 4.25. Where's my square root button? Second square root. Shoot. Second square root, 4.25 equals final velocity equals 2.06155528 and more on all this kind of good stuff. So there's my final velocity. So my final velocity, 2.06 go in this direction, right? My VF is now going the same direction. VF is still going that way, so that works. And I need to do sig figs in units. Okay, sig figs, look at the problem. Remember, you're almost always, pretty much always, using the least number of sig figs in your answer. That was in the problem. You have to go with the least level of precision. So what do we have here? I've got 3 sig figs up in the 2.50. This has 2 sig figs. Leader zeros never count. Follower zeros are precision zeros. So this one only has 2 sig figs. This one here has 3 sig figs. That means that my final answer has to have 2 sig figs because I go with the least precision. So I'm going to look at my answer down here. It means I can round it to 2.1. And then it's a VF, so I have to use units consistent with VF, which is meters per second. So that would be a perfect answer at the end. So again, picture your problem, identify your variables, figure out which equation matches those variables, plug in your numbers and go. All right, moving on. So I think I have five examples of this using different equations. One of them, if you think you're good and you don't really need a lot of help with this, fast forward in this video to the last one, which is called hitting the brakes problems, because those are a little bit different and most students don't know how to do that part. So if you're good with equations, you're good with plug and chug, fabulous. Feel free to pause and fast forward to the later part of this. I'll go through the rest of these problems. But again, if you're good at this, make sure you go to the last problem that I do in here, which is called hitting the brakes, and double check that one. It's got a picture of a cat on the corner because, you know, cats, right? So here's example number 2. We got a race car going, traveling at 44 meters per second and slows at a constant rate to a velocity of 22 meters per second over 11 seconds. How far does it move during this time? Okay, what are we trying to find? So I've got a race car. There he is, race car. There he is. He's going that direction. He's traveling at 44 meters per second. So plus 44 meters per second is my VI. That's what he's starting at. Slows at a constant rate to a velocity of 22 meters per second. So that's going to be my VF plus 22 meters per second. So there's some sort of acceleration going on. My acceleration must be going this way, right? Just because I can tell if it's slowing down, my acceleration is got to be in the opposite direction. And its time here is time equals 11 seconds. How far does it move? How far is a displacement? I want to know what its DF is in terms of how far that it's going. Okay, so what do we have that would work for this? So we have a VI equals 44 meters per second. We have VF equals 22 meters per second. We have T equals 11 seconds, and we're trying to find D. So what equation do we have that might work for this? Do we have one equation? Do we have 2 equations? How can we figure out what this is? So let's take a look back at our kinematics page and seeing what we've got that'll kind of take care of these things. VI, VF, T, and D. All right, let's go back. Hold on. Here we go. VI, VF, T, and D are the ones that we have in our current one. VI, VF, T, and D. Those are the ones we've got, so we could use this to find delta V. So do we have any equations that work for this? Well, that one will give us acceleration. That one will give us displacement, and we've got time. We just need acceleration for it. This one's got VF, VI, acceleration to displacement. So it doesn't look like any of these really work easily for us, right? There isn't a single equation that has those components in it. Don't get suckered into using this one. This is what everyone wants to do. Okay, velocity is distance divided by time. Oh, I can just put them right in here. That's going to be a delta V, delta dt. I'll just use that one. Can't use that, and that's why I specifically put this example in here. Remember, this top equation is only used when there's no accelerating. This one definitely is accelerating, so you are not allowed to use that top one. So this is actually going to be a 2-part problem. If I don't have a single equation that'll work, crud, maybe I have to use a 2-part problem. So maybe what I'll do is I'll do this one first, right? Because I've got VI, VF, and T. Can use that to figure out what acceleration is. And then I can plug acceleration in one of these other ones to figure out what my displacement is. Like I might plug it into this second one to figure out what my displacement is. Or you can plug it in the bottom one. Doesn't really matter. There's actually more than one solution to this. So hold on, there we go. VF equals VI plus A delta T. That's the equation that I can use to find my acceleration. Since I don't have it yet, okay, fine, let's do that. VF is 22. Plug them in the right spot. VI equals 44. Make sure that you plug them in the right spot. It's important. plus a times 11, because my time was 11. Make sure that you plug them in the right spot. So when I start solving for this, I'm going to move my VI over to the other side, subtract 44 from both sides. So 22 minus 44 equals 11a, right? 11a. Okay, this is negative 22 equals 11a. My acceleration is negative 2. That's what that means. If you did this backwards, by the way, you get an acceleration that was positive. It would look like it was speeding up as opposed to actually giving you acceleration that's slowing down. So now we know what our acceleration is, negative 2 meters per second squared. I know we're being a little sloppy about Sig Figs here because we're going to take care of that at the end. I didn't round anything to get this. It's an even whole number, so we don't have to worry about it too much. So now do we have an equation that we can use with these things? Yeah, we actually have choices. Truly, we have choices. Sorry, went the wrong way. Now you could either use this bottom one, because you have enough to do that, or this top one. You have enough to use both of them. It does not matter which one you do, because both of them have distance in there, and it's totally fine which one you want. Maybe I'll use this bottom one here just because I can. We'll use the top one here in a little bit as well. Does not matter. Again, one of the nice things about this with kinematics, a lot of times there's more than one path. And that's totally fine. This one's a little easier to remember, so I'm going to use that bottom one just because, I don't know, I guess I like it. There is where I want to be. So VF squared, hold on, sorry, pen. VF squared equals VI squared plus 2A delta D. So I know what my VF squared, my VF is 22. My VI is 44. Squared. Again, I'm looking over here at my list of variables. This is more useful than you may want to think it is. 2 times my acceleration, which is negative 2 times d, times delta d, or my change in displacement. So now I can start doing a little bit of math. 22 squared, get my calculator on. 22 squared is 484. This is 484. 44 squared is 1936, and this becomes negative 4 times d, not minus 4, but it's 2 times negative 2 is negative 4. All right, so let's do some algebra. Let's move this guy over here. Subtract 1936 from both sides. So 484 minus 1936. 1936. I'm dyslexic, so I have to kind of double check everything I do 3 times. My apologies. So I get negative 1452 equals negative 4d. So now I can divide my answer by 4. And 1452 divided by negative 4, right? Divide by negative 4 both sides, gives me an answer of 363 equals d. And that would be 363 meters equals our displacement. That's my units because it's a displacement to it. All right, sig figs, 2 sig figs. There's 2 sig figs here, 2 sig figs here, 2 sig figs here. We got to write that as 2 sig figs. So we would write that as 360 meters equals our displacement. There you go. There's a final answer. You could also write this as 3.60 times 10 to the second. If you want to write it in scientific notation, not 3.60, 3.6 times 10 to the second gives you 2 decimal places, or 2 sig figs as well. They both work, as long as you put the units in there, meters. All right, moving on. Example number 3, coming up. All right, we've got an airplane accelerates down a runway, 32.8 seconds, finally lifts off the ground. How far did it travel? Again, we're trying to find a displacement to it. So we've got an acceleration. I'm not sure how I would draw a plane. Plane like this. There's its wing. There's its other wing. It's accelerating this way, right? So there we go. So it's accelerating down the runway. A equals 3.20. Its time is 32.8 seconds. And it's going to eventually lift off. And then we're trying to find displacement, right? So A equals 3.20 meters per second squared. Time equals 32.8 seconds. Lifts off the ground. How far did it travel before it goes? I'm trying to figure that. So here's one of the things that we're missing in this particular equation. There's a kind of a hidden thing on here, and I want to mention this. What's VI? We don't know VF. We know that it's taking off the ground, but we don't know what its final velocity is. But there is a hidden piece that's in here that happens a lot in these. So one of the things you want to look for is little hints about what VI or VF is. When you're talking about it starts from at rest, it's accelerating down a runway. It's starting at 0 meters per second. We don't know what its VF is. And I don't think we need to know it for this one. But you get this a lot with cars coming to a stop, cars starting from rest. Sometimes they will say it's starting from rest, sometimes they don't. So again, here, it had to be starting from somewhere. It's accelerating down a runway. If it doesn't give you a VI, it's probably a good bet that its VI is 0. So do we have an equation that has these in here? Yeah, it's a long one. So DF equals DI or DO plus VI delta T plus 1/2 A delta T squared. And that has enough in there. Again, you can go look back at your list of equations. This has got all the pieces in there. We've got time to use, so we don't need to use the VF squared one. And we don't need to use the VF equals VI plus A delta T, because that one doesn't have distance in it. So that one doesn't do us any good either. So this equation that we've got here is the one that's got the missing pieces. So here's the good news. DI, well, it started at position equals 0. A lot of times that goes away, unless there's some specific comment in there. Usually that's 0. What's our VI? Well, our VI is also 0, right? So VI times T also becomes 0. So DF equals 1/2 A delta T squared. And we have plenty of information there to be able to figure that. 1/2 times 3.20 times 32.8. And then don't forget to square it. Again, the two things that really smart students do repeatedly in this chapter is drop negative signs and forget to square things or unsquare things. So they drop that squared part in there. So 32.8 squared is like 107. 1/2 times 3.20 times 107.5.8. 107.5.8, hard numbers for me to write, and then multiply those together. So times 3.20 and times 0.5. And again, I'm double checking myself because me and dyslexia, it's hard. So I get this 1721.344. Again, that's kind of what I got on there. So we'll see how that works. All right, so what does this mean? Sig Figs, units, round it, get it done. 3 Sig Figs in this problem, 3 Sig Figs in this problem, so we can write our answer in 3 Sig Figs. So what would that be? 1720, like that. That would be our 3 Sig Figs. Trailing zeros without a decimal place don't count. That's just a placeholder 0. And then we want to use meters per second. Units, what are we doing? How far did it travel? How far is a displacement? So our final answer is going to be in meters. And it traveled 1720 meters. That's 3 Sig Figs in final units. All right, so here's our last one. This is our hitting the brakes problem. And these are a little bit hard simply because they are two-part motion. And again, so I wanted to mention how this particular one works because, again, it's one of those ones that sometimes can throw students off. So here we've got a question. Again, there's a variety of these. There's questions like reaction times questions, like you see something, you're driving along, you see something pop out in front of your car. And it takes you a certain amount of time before you hit the brakes. And then after you hit the brakes, you slow down. Or, like I said, reaction time is a really common, or like in this particular case, we've got our cat is running for a certain amount of time and then he's skidding for a stop. So we've got two-part motion on this. So our cat's actually doing two different things. I'm going to do this as a velocity time graph actually for a second, so I can kind of show you what this looks like. He's running along at 2 meters per second for a little while, and then he skids to a stop. So we've got two-part motion in here. We can't use one equation for this. We can use one equation for the first half of his motion. It's area under the graph, right? And then we can do a different equation for the second half of this. And that's the important part of hitting the brakes problems. Two-part motion requires two-part solution. So that's what you want to be kind of paying attention to. So our cat's running at 2 meters per second for 3 seconds. How far did it go during that? That's part one. And then it skids to a stop with its acceleration of negative 0.8 meters per second. That, hello cat, speaking of, is part two. And then we add those two things together to combine them. So in the first part one, this is constant velocity. He's just running at 2 meters per second. Velocity equals displacement divided by time. Or we can do it this way. VT equals D, right? Velocity times time equals distance. So how fast is he going? 2.0 meters per second times 3 seconds gives us a displacement of, math geniuses, 6 meters. How far it went in part 1. Part 2. This is the deceleration phase. So what do we know about this? It's deceleration phase. We know what VI is. He's starting at 2 meters per second. We also know his final velocity. He's skidding to a stop. VF equals 0 meters per second. And we know his acceleration. A equals negative 8.80 meters per second squared. And we want to know displacement for this one. So we can figure out how far it went during this second part of its motion. Do we have an equation that's got VI, VF, A, and D with no time in it? We do not know how long it took for it to stop here. We know this first part was 3 seconds. We do not know the time in the second part. That's important here. He ran for 3 seconds. Then he skidded to a stop. That 3 seconds does not apply to the second part. So in our second part of our motion, we have to use a different equation. This is VF squared. Ain't got no time for that. VI squared plus 2A delta D. Again, we don't know the time for this one. That 3 seconds was during its constant motion phase. So VF equals 0. That's kind of nice. VI equals 2 squared plus 2 times the acceleration. Don't drop the negative sign. Negative 0.8. And then displacement. So what do we got? 2 squared is 4. I know that. I don't need a calculator for that. 2 times negative 8 minus 1.6 times D. So 0, right? 0 squared. So negative 4 equals negative 1.6 times D. So negative 4 divided by negative 1.6 gives me an answer of 2.5. So D here equals 2.5 meters. Okay, this is positive. He's still going forward. That makes a difference. If I didn't have the negative sign in here, it would be like he went forward and then somehow he changed his direction, was going backwards somehow. That would be a pretty amazing cat, that somehow it just skidded and reversed its course without doing anything else weird. So the signs here do make a difference. So what was its total displacement? Its total displacement was 6.0 meters plus 2.5 meters in the same direction. Total displacement is 8.5 meters total during its motion. And we've got 2 sig figs all the way along, so 8.5 meters is consistent. So there you go. That's a hitting the brakes problem. Again, so making sure that you're analyzing that 2-part motion as 2 separate events, part A, part B, and then combine them all together. And that makes a difference. So there you go. I hope that helped you kind of start to get an idea of how to attack some of these kinematics problems, how to use sketches to help you, how to identify variables, and how to use those variables to identify. Sometimes there's a sneaky 2-part problem in there. And don't be panicking if that's happening. But don't use an equation you can't use either, okay? There you go. See you guys in the next bit. I think we do free fall next. Free fall like your grades? I hope not. See you guys. Bye.